Hey everyone, and welcome. There's this hidden logic that's running pretty much everything around us, from the simplest little gadgets in your kitchen to some of the most complex tech on the planet. Today, we're going to pull back the curtain and dive into what are called control systems.
I mean, think about it for a second. It kind of feels like magic, right? You just punch in a number, and your house just does what you want. But of course, it's not magic. It's actually a really brilliant piece of engineering. So how does it work? How does it know? Well, the answer, the secret sauce behind it all, is something called a control system. It's basically the brains of the operation. It's what makes everything from the cruise control in your car to those giant industrial robots work so smoothly and automatically.
All right, so let's break this down. What exactly is a control system when you get right down to it?
At its heart, it's actually pretty simple. A control system is just a way of arranging different parts so that you get the result you want. That's it. It's not about one single component, but about how a whole team of components are designed to work together to hit a very specific goal.
And really, they all follow this basic three-step dance. First, you've got your input. That's your command, right? It's what you want to happen. Then, the control system takes over. It's the part that does the thinking. And finally, you get the output, which is the actual result. Input, process, output. This simple flow is the blueprint for everything else we're going to talk about.
Okay, so let's look at our first type of system, the most basic one out there. We're talking about open-loop systems.
The easiest way to think about this is the set-it-and-forget-it approach. Like a simple toaster. You pop the bread in, you push the lever down, and you walk away. The toaster does its thing, but here's the key. It has no idea if your toast is perfectly golden or a burnt piece of charcoal. It just runs the command, and that's it.
And that gets to the absolute core of open-loop systems. There is no feedback. The controller sends out the command and just hopes for the best. It assumes the job got done right. Now, this makes them really simple and cheap to build, which is great, but the downside is they're not very accurate. If something unexpected happens, say a little power surge, the system can't adapt. It has no way of knowing that something went wrong. A perfect example is a basic street light. It's on a timer, right? That's the input. So at 7 p.m., boom, the light comes on. It doesn't matter if it's a super bright summer evening or a dark, rainy afternoon. The light doesn't check. It just follows that one initial command. Classic set it and forget it.
But, okay, what if good enough isn't actually good enough? What if you need something way more precise? Something that can actually adapt? Well, that's where we get to the next level. The much, much smarter closed-loop system. Now, this is a total game changer. Closed-loop systems have a kind of superpower that open-loop systems are missing, and that superpower is called feedback. Honestly, this one simple idea, the ability for a system to check its own work and self-correct, was a massive leap forward.
So here's the magic. It uses a sensor to actually measure what's happening, the output. Then it sends that information back to the controller. The controller looks at that and compares it to what you wanted to happen. If there's a gap, what we call an error, it automatically tweaks things to fix it. It's this constant loop of measure, compare, adjust, measure, compare, adjust. And that's what makes these systems so incredibly accurate and stable.
And here we are, right back where we started, with our thermostat. This is exactly how it works. It has a little sensor that's constantly checking the room's temperature. That's the output. It compares that to the temperature you set on the dial. Is it getting too hot? Okay, it kicks on the AC. Is it getting too chilly? It turns it off. It is always checking and adjusting. That, my friends, is a perfect closed-loop system.
So putting them side by side really makes it clear. You can see it all comes down to that first line, feedback. One has it, one doesn't. And that one little difference changes everything else. Open loop? Simple, low cost, but not super accurate. Closed loop? Yeah, it's more complex, but you get way higher accuracy and it's much more stable. It's a classic trade-off, really.
Okay, but what if we could get even smarter? What if a system could fix a problem before it even happens? Well, let's take a quick peek at an even more advanced idea, the feed-forward system.
This is where things get really cool, because this is all about prediction. Instead of waiting for an error to happen and then reacting to it, a feed-forward system tries to predict that something's about to go wrong, and it takes action ahead of time. It's proactive instead of reactive. Now, for this to work, you obviously need a really good way of predicting what's going to happen, which is why it's often combined with a feedback system just to be safe.
A great modern example is a smart sprinkler system. It doesn't wait for a rain sensor to say, hey, the ground is already soaking wet. No, it's smarter than that. It checks the weather forecast. That's the prediction. It sees that rain is on the way tomorrow, and based on that prediction, it takes action now and cancels the watering schedule. It prevents the error of overwatering before it can even happen. That's feed-forward control.
Okay, we've looked at the different types, which is cool. But let's zoom out for a second. Why does any of this actually matter? Why are these systems so critical to our everyday lives? Because the benefits are literally all around us, woven into everything we do. Think about safety. The anti-lock brakes in your car. That's a control system reacting faster than any human possibly could. Or accuracy. The only reason we can make things like computer chips is because of the incredible precision of control systems. Energy savings? Your thermostat is just one example. Entire power grids rely on these systems to be efficient. And stability. From keeping a jumbo jet flying smoothly in rough air to making sure your Wi-Fi signal doesn't drop. These things are the quiet, unsung heroes working behind the scenes 24/7.
And it all circles back to that core idea we started with. It's about designing things with purpose. It's about arranging components in just the right way to get exactly the result you want, every single time.
So that kind of leaves us with one final question to chew on. We've gone from simple timers to systems that react, and now to systems that can predict. As our world gets more and more connected, what's the next step? What kinds of problems will the next generation of control systems learn to solve before we even realize there's a problem? It's pretty amazing to think about. Thanks for joining me.